to the Prussian Academy of Sciences, and it has a very deep thought in it. He says what he called the Weil-Streckenfaktor. He said, if I have a sphere and I do parallel transport of a vector, and I move it along a triangle, and then I bring it back, then because of the curvature of the sphere, the vector that I started from has changed its orientation. And it will not point in the same direction as it did before. That is well known. That is a measure of the curvature, and is, of course, at the very heart of relativity. However, Weil said, wouldn't it be interesting if also the length of this vector changes as I propagate it around? So it's not only the orientation of this vector is different, but also its length has changed, as indicated in this diagram. And he proposed a rule according to which this vector should change its length. And he said, okay, I take the vector potential with its 4 components, and I propagate it on this sphere or in this metric space. And of course, there must be the elementary charge, because this is how I couple a particle to an electromagnetic field. And there is a coupling constant involved. And he says, I don't quite know what that coupling constant is. It is gamma. And I call it gamma. And he didn't know about what it would be. Now, it's interesting because the paper that he submitted to the Prussian Academy was, of course, refereed by Einstein. And Einstein did not agree with the paper and the conclusions, but he allowed to publish the paper. And he wrote then a rebuttal and explained why the paper is wrong. Now, I don't want to get into the discussion what was wrong, what was right there. But at the same time, Schrödinger wrote a paper about this. And he said, there's a remarkable property of an electron moving on a Sommerfeld or Bohr trajectory. And he calculated the Streckenfaktor of Hermann Weil for an electron in a hydrogen atom. And he noticed something very interesting. He noticed that it's an integer multiple of h bar. And so in this very paper at the end, he suspects that maybe this constant that Hermann Weil did not know would be h bar, but a square root of -1. And in this sense, the length change that Hermann Weil was talking about has nothing to do with the length change, but a phase change. And in that sense, this idea of Schrödinger came in very early. And you noticed, as I said, it came in 1922. So 3 or 4 years before quantum mechanics was invented. It goes without saying that quantum mechanics, in some sense, was invented even before it was invented, also in Munich. Now, what do I mean by that? We all know Feynman's famous approach towards quantum mechanics based on the path integral, where we have in space-time all trajectories interfering with weights given by the classical action. Let me say and emphasize that this idea, and of course Feynman deserves the credit, however, this gentleman, Gregor Wenzel, who was a Privatdozent in Munich in 1924, again, before quantum mechanics was really found, real quantum mechanics. I'm not talking about the Bohr-Sommerfeld quantum mechanics, but this guy Wenzel wrote a paper in Zeitschrift für Physik entitled Zur Quantenoptik, which means on quantum optics. And I think this is even the first time that the name quantum optics appears in the literature. Now, what did he do? Wenzel talked about an atom at a given position emitting light, the light propagating on a path towards another atom, and the atom being the photon being absorbed by the second atom. And then he calculates what is the probability for the light to go from one atom to the other atom, or in the other language, what's the probability of finding the atom, the second atom, the absorbing atom, being in excited state. And he says very clearly in this German text that the probability is not just the probability of the individual paths, the sum of these paths, but it is the sum of the probability amplitudes. As you see here, the square here enters as the sum of these phase factors. So in some sense, that was the beginning of the path integral. So after these historic notes, I now come to this mathematical identity that you can find in this paper with Danny Greenberger and Don Kobe and Wallen Scully. Now, what is this mathematical identity? If you have a complex function, capital Z, that depends on the coordinate and time, then of course this complex function can be represented by an amplitude and a phase factor, which of course will also depend on coordinate and time. Now let's assume you want to have a differential equation which is first order in time and second order in position. Now you might wonder, why do you want to even talk about first and second order? Well, you could argue if it's an electromagnetic wave, it must be second order in time, it must be second order in space. So if you want to get something new, you change, for example, the time derivative from second derivative into first derivative. And you ask yourself, can I just get an equation in which I have the first derivative in time and the second derivative in time? Now, of course, the units of these derivatives don't match, so you're going to have a new constant beta coming in order to make these derivatives match. And it turns out if you put the I in here in front of the derivative in Z, then all this of a complex function, all these derivatives of a complex function can be expressed in derivatives of amplitude and phase. And as I say, this has nothing to do really with physics at this moment. It only has to do with expressions in terms of derivatives of amplitudes and phases. And you notice when you look carefully here, this looks almost like a continuity equation. This is like an intensity, time derivative of an intensity. And here you see there's the divergence of an intensity times the gradient. So as a result, what you see here is a continuity equation for a density and for a kind of velocity. At the same time, you see down here that this is like the Hamilton-Jacobi differential equation, which involves the time derivative and the gradient of the phase squared. But of course, there's also a third contribution coming in, which is the Laplacian of A divided by A. And now you can see how one can get to the Schrödinger equation. So the first thing you have to assume is that you're dealing with a wave equation that is second order in position and first order in time. But you will need a little bit more because so far you really haven't involved physics. You have to find how this equation goes from the quantum world to the classical world. So these are the thoughts that we have to rely on in order to get the Schrödinger equation. So let me go back and say, okay, in classical Hamilton-Jacobi formulation, or I should rather say in a formulation of classical mechanics in terms of a Hamilton-Jacobi equation, you would have an action, a classical action, that depends on coordinate and time, but it also has a constant of motion in there. And of course, the underlying equation is this equation here, where the momentum comes from this field by taking the gradient. And from this, I can also derive what Van Vleck did in his paper of 1928, a continuity equation. Namely, the continuity equation by just taking this particular equation and defining what is called today the Van Vleck determinant. Namely, we take the classical action, differentiate with respect to a given coordinate xk, and differentiate with respect to a given constant of motion epsilon j. Needless to say, this object is a matrix, and we can easily calculate from the matrix the determinant. Once we have the determinant, we can use the equation of motion for the action, which of course appears in the definition of D. And surprisingly, we find this particular continuity equation. So it is exactly a density, the divergence of the density times the gradient over M. So we have a continuity equation, which is implied by the Hamilton-Jacobi equation. And now we can go back into the mathematical identity that I showed you earlier and just simplify it. So I said this equation here, having the right constant, will be 0. This term and this term is going to be replaced by the velocity if we assume Hamilton-Jacobi dynamics. So then this term vanishes. This term compensates this and brings in the velocity. Then this term here on the right-hand side survives. And of course, now we get an equation of motion for a complex function psi, which is defined now in a very tricky way. So we define a wave function psi, and I put in the word classical in order to explain or remind myself in your presence that this is not quantum mechanics. The amplitude of this wave is the square root of that particular density, the von Vleck determinant. And then the phase of this function is the action, the classical action. And of course, as I said, if I take that ansatz, then the mathematical identity leads me immediately to this equation, which is almost the Schrödinger equation, except now it has here what you would naively think the quantum potential. This is interesting because you're describing classical statistical mechanics in terms of a wave function. And in terms of a wave function that appears in a nonlinear way in this particular wave equation. So what we see is that classical mechanics can be described as a wave equation, but it is a nonlinear wave equation. This has been noticed for the first time by Ralph Schiller and of course Nathan Rosen in some remarkable papers, and Schiller has a whole series of describing and working on these equations. Now, going back, we said, well, how do we get to the Schrödinger equation then? Well, if we have a continuity equation underlying this wave, and we do not replace just this by classical Hamiltonian equations, but we combine an equation of motion for theta in such a way that also this term is absorbed, then of course, this term is canceled because of continuity. This term here is replaced by potential, and we will arrive at the Schrödinger equation. So very easy. We now define a new wave, and it has a superscript Q in it, which has the phase here. And that phase now satisfies an equation so that we arrive at the linear Schrödinger equation. And that leads us in a very simple way to this. So now you see when you compare classical and quantum, you notice that in classical physics, you have an equation of motion that determines automatically the continuity equation. This equation implies this. And what you notice is that, yes, the density D is driven by the phase, and in particular, the gradient of the phase. But you notice that there's an asymmetry in classical physics. The equation of motion for the phase is not coupled to the density. In contrast, in quantum mechanics, we have a symmetry between the amplitudes and the phases, in the sense that here we have the phase being determined by the amplitude of the wave and the amplitude being determined by the phase of the wave. So the clear distinction between the classical description, classical statistical mechanics and quantum mechanics is the way these two equations are coupled. And now I want to stop here and summarize, so to speak, that the key thing that I told you is this curious, what I call curious mathematical identity, valid for any complex function being represented either in amplitude and phase or as the complex function directly. And depending on how you distribute, in some sense, this nonlinear term in this mathematical identity, you can either take it into the classical wave, then you get a nonlinear wave equation, or you put it into the phase equation. That's what, for example, Madelung and Bohm did. Then you get quantum waves. So either the wave equation is nonlinear, then you have classical matter waves, or the equation is linear, then you have the quantum matter waves. So with this, I go over now to the Wigner approach, and I have a few minutes left for that. I see I have still 10 minutes to go through that. And as I said, I have essentially two things that I want to emphasize to you: Wigner functions in higher dimensions and tunneling. But again, I want to provide a little introduction and make the connection in particular to this discussion of the wave equation. Now you might say, why is it that from the very onset, I wanted to have a complex valued function? Why did I look for a mathematical identity of complex functions? And the answer is because classical statistical mechanics already involves two equations, because it lives really in phase space. So we need two independent variables like position and momentum. And of course, phase, as we learn already from this Hamiltonian discussion that I presented, the phase in itself is the derivative, or I should rather say the momentum is the derivative of the phase with respect to the coordinate. So you need the density, which has to do with the amplitude, and you need the phase, which has to do with the momentum. So you really need two equations which govern the dynamics, one that has to do with position, one that has to do with momentum. And that's why you need a two-component function, two real valued functions, and combining them into one complex function allows you to get rid of a nonlinearity in amplitude and phase, which is linear, and you'll get rid of a nonlinearity, which eventually leads you to a linear equation. Now, of course, for this reason, it is natural to go and look at an equation that lives in phase space, either here in coordinate and velocity, or as Wigner said in this particular paper of 1932, construct an object that consists of a bilinear combination of the wave function. So take the wave function, shift the coordinate by one variable y, and shift the wave function in the opposite direction in the other wave function, and then take the Fourier transform with respect to these shifts. Then you're going to get a function that depends on coordinates. And you notice this is already in the original paper with several variables. And here you see the momentum that enters as the variable that arises due to the Fourier transform.
So you have 10 minutes to the end, including questions.
Thank you very much. And I think I'm perfectly in time. There's an interesting remark down here. This is a picture of Wigner at the time of the 1930s. This is, of course, later. But here's a little remark that he made where he got the idea from. And he says, this expression was found by Leo Szilard and the present authors some years ago for another purpose. Now, what is interesting is that I learned from Bob O'Connell, who had worked extensively with Wigner, that this paper does not exist, and it never existed. And Wigner once said Szilard was looking for a job, and he thought this remark might help Szilard find a job. So interesting remark there. In one dimension, of course, Wigner functions are very simple. Here is the shift in the one variable. Here it is in the opposite direction, and here is this Fourier transform. And of course, if I integrate, for example, over momentum, then this integration over the variable momentum would give me here a delta function, and this shift here would disappear, and I get just the probability. Another interesting property is that the Wigner function allows you to propagate in time as in classical physics, as long as you're talking about the free particle. So there's no quantum mechanics, by the way, in the free propagation of a particle. So no quantum mechanics. The only quantum mechanics is in the initial state. So the next step is, as I said here, the time evolution. And this fact that free particles or even harmonic oscillators have classical time evolution stands out most clearly if you take the commutator between H and energy. And what you will find is that the Liouville equation, which I showed you only very briefly at the beginning, has a quantum correction term in it. This would be the classical Liouville part. This is the correction to it. And you see, this involves powers of H bar, but it also involves derivatives of the potential. And if this potential is quadratic, no such quantum corrections appear. Of course, if it is linear, no corrections appear. If the potential is zero, obviously no corrections occur. What is also interesting in this context is that you can transform the energy eigenvalue equation, the independent Schrödinger equation. You can transform that also into a system of phase space equations, and then you get like the eigenvalue equation in phase space. Now, even for a harmonic oscillator, H bar appears explicitly. So what I'm trying to argue here is you do not need to go through the wave function in order to find a formulation of quantum mechanics. The wave function is not needed. There are enough equations to determine everything in Wigner phase space. Even the area is defined. The area of the minimal area that is allowed of a quantum state is defined in terms of the square of the Wigner function. But I don't want to go through it. You're all familiar that Wigner functions can assume negative values and that the interference property is determined by this. Serge Haroche in Paris did beautiful experiments on the decay of Schrödinger cats, and these are measured Wigner functions. Measured Wigner functions where you have a coherent state here and a coherent state here, and you see these interference fringes, which are, of course, a feature of the bilinearity of the wave function. The free propagation of such Wigner functions shows you very clearly that you get focusing. And even if the Wigner function is negative at the beginning, you can use this to produce very unusual focusing effects that I don't want to dwell on. Let me just come to the very end of everything. Together with my friend Jens Peter Dale, who was a professor in Copenhagen and who has done beautiful work on Wigner functions. He was the first to calculate the Wigner function of the ground state of the hydrogen atom. We try to understand higher dimensional systems, like, for example, the ground state of the wave function. And you might think naively, since the wave function, psi of a radial wave function, will only depend on the radius on one variable, well, maybe the phase space is only two-dimensional because the conjugate variable might be just the radial momentum. But of course, the experts in this group know there is no such thing as a radial momentum in an easy way. But Wigner himself has given the answer in his original paper. He said, Wigner functions can be defined in arbitrary dimensions. So all you need to do is remember that the Wigner function, the wave function psi of r is really psi of the square root of x1 squared plus x2 squared plus x3 squared. And then you can use this definition, and then you will find something beautiful. You will find that even for an S wave, for an angular momentum zero eigenstate, the phase space is already three-dimensional. It depends on the radial variable, on the absolute value of the momentum, and it depends on the angle between radius r and p. So these variables enter in this way. So let me go on to the last point, tunneling. Simple case of an inverted harmonic oscillator. And what we know is that if you have the energy down here, then the trajectory, the classical trajectory, corresponds to a motion coming in and being reflected from this potential. This motion here above the barrier is just the motion going in phase space here. And of course, zero energy coming in here, the particle would just end and it stops here at this point. Now, there's no way you can ever enter this area down here and cross this line. So in some sense, we have a horizon, but not a horizon in configuration space or in space-time, but a horizon in phase space. But what is beautiful, you can now solve these energy eigenvalue equations that I showed you before. And what you will find is that tunneling is because the Wigner function is not restricted, and I don't know, to this domain here, but the Wigner function is restricted to this domain here and here. And the tunneling is achieved by non-zero probability for trajectories just running above the barrier. And with this, I think I come to the end. You can solve this, and you will see this is the Wigner function for an energy eigenstate with tunneling. This would be like the classically trajectory that you would expect. But you notice also for trajectories running above the barrier, you have non-zero probability. The Wigner function is expressed in this integral here. And you notice an interesting fact. It involves a logarithmic phase singularity. Here's a phase, and this phase involves a logarithm. And this is very similar to the Hawking radiation that appears in horizons not in space-time, but here, of course, it's a logarithmic phase singularity in phase space. So we also have the connection there. And with this, I come to the end. I thank you very much. I want to thank the organizers for giving me an opportunity to bring all this work to the discussions here. And I look forward to a few questions. Thank you very much.
Okay, thanks. Thank you very much for this interesting talk. Questions. I would encourage the audience to ask questions and start interacting.
But do not ask me to bring the transparencies back.
I would have actually two questions. I'm Giovanni Manfredi from Strasbourg, if it's okay for the chairman.
Yeah,
absolutely. Yes, go ahead. Yeah.
You've shown this classical version of the Schrödinger equation with the nonlinearity, where you have the quantum potential. So basically, that means you add the quantum potential there, which actually cancels it out when you go back to the kind of Madelung formulation.
See,
maybe I just my way to formulate it, but it's the same as you.
Yeah, see, my point is the following. If you agree on certain orders of differential equations, certain derivatives appearing in a wave equation, depending on how you couple amplitude and phase of these two equations, depending on this coupling, you get classical statistical mechanics or you get quantum mechanics.
No, I agree with that.
That's how I look at the point. It might not be a very deep insight, but for me, it was revealing that one equation contains both limits. Okay, it's
actually my question was: do you think it can have any practical use? Because we know that this representation runs into problems. For instance, where the wave function has nodes. You divide by psi. You have this quantum potential that is undefined at nodes of the wave function. So can it be? Do you think it can be used in a practical context?
I would have thought so. Yes, it can be. In my opinion, it can be.
Okay. And then very briefly, right in the beginning, you've shown the original paper by Schrödinger on the time-independent equation. What is the reference for the second paper, the time-dependent one? I missed
it. Was also in Annalen der Physik, but I can send you the slides. I guess we have the slides available, don't we?
We would collect the slides if the speakers want.
So you want me to send you the slides, or to whom do I send the slides?
We will let you know by email.
Okay, so you can have the slides, Giovanni.
Thank you.
You can have the slides, but if you go to the paper, there's, if you want, I can also send you a paper, I mean, which we wrote for the Varena lectures that Stefan Jorda was showing earlier. We had a conference on quantum theory in Varena, and there I wrote the whole approach up in a different way with a lot of more historic notes. So whoever is interested, I can send this paper. Maybe we can put up, Cesar, a website where we can just deposit these papers, and then everybody can have a look at them.
Okay.
Yeah.
Yes, please.
Okay, we have another maybe quick question from Aurelia.
Hi, thank you. Thank you very much for the beautiful presentation. I'm Aurelia Chinnu from University of Luxembourg. I was wondering, in your derivation of the Wigner function, it was not clear to me how the classical and quantum difference appears. Can you see like somehow like negativity for the Wigner function in the quantum realm, or are the equations like absolutely equal?
Okay, so I'm not sure if I understood the question completely. So, let me understand two things. There are two parts to the thing, and that I always felt that in the Wigner function approach, it is much clearer than it is in the Schrödinger formulation. There are two parts to it. There is quantum kinematics, and there is quantum dynamics. And there are cases in which you have no quantum dynamics, and all the quantum mechanics sits in the initial condition. So, as I mentioned, in the free motion, if you would solve the Schrödinger equation, you wouldn't see that this is classical mechanics, but it's not classical mechanics in phase space. It's classical mechanics somehow wrapped in a funny way in coordinate space. Whereas in the Wigner function, you see clearly the only quantum mechanics sits in the initial condition, but not in the dynamics. Now, you also asked me about the derivation of the Wigner function. Now, there is a derivation that you'll find in my, not a derivation, a motivation in my book, in which you have the following argument. You say you have a jump in quantum mechanics, you jump from one position to another position. So you express, you do not work with one coordinate, but you work with two coordinates, one before the jump and one after the jump. And then there is the jump. It involves, of course, a momentum to go from here to here. And then you replace the coordinates going from here to here by the center of the coordinate and the jump lengths. You Fourier transform the jump lengths. That's how you get the momentum involved. And the center, the classical coordinate x, is then the center of the jump. So I'm not sure if I answered any of the questions, but at least I thought I could give you a little bit of a feeling.